Thank you for the opportunity to talk to you about external static pressure. I just want to do a quick preface showing why we do the static pressure reading and show an example of a blower performance chart and the relationship between the two. In the ductwork class, we go a little more in depth on how we get the static pressure and why we need a certain static pressure. But I wanted to just kind of reinforce the idea, what we're looking for, why we're looking for those numbers. And when I do ask for them, why I ask for them, what we can do with them once we get them. Let's go ahead and jump into the module. Hopefully it answers any questions you have on external static pressure, or at least a good foundation on the ESP. The external static pressure reading will be everything on the input of the equipment and the output of the equipment for the positive. So the evaporation coil on a gas furnace is not part of the equipment. The reading would be taken between the furnace and the evaporation coil, and on the input between the blower and the filter. This is an example on a gas furnace. The positive pressure being 0.4 would be under the evaporation coil, and the negative pressure between the filter and the blower would be at negative 0.2. And we'd look at the difference between the two, and we'd find that would be 0.6 inches external static pressure. These numbers are important to assure proper operation. We look at the rating of the equipment. The rating of this equipment is rated at a 0.5 inches for total external static pressure. When we do take the reading, in this case, if we had a 0.5, when we had a 2.5 ton system, we'd set it for speed 7. If our static pressure was 0.8, we'd have to adjust the speed setting to speed 8. After we make an adjustment, we'll remeasure our external static pressure. This is an example of a manual J being completed. And let's say we find we need a 3 ton for a home. We'll look at our matches and we'll see we have different equipment we can choose. We also have different coils. We'll choose one and get a ARI number. And once we have that, we'll look at expanded ratings and take a little closer look here at what happens with those expanded ratings. As we zoom in on a section of it, you'll notice at a 95-degree outdoor temperature across the top, indoor temperature, dry bulb of 75 and a wet bulb of 63. And we're choosing 1200 CFM per our AHRI for 3 ton. You'll see our output is 31,100 BTUs total with a sensible heat ratio of 0.82. We'll also see a delta T, kilowatt rating, our amp draw, and our high and low pressure expected at that operation. Let's look closely at that sensible heat ratio at a 0.82. You'll see 82% will be for the sensible load, which is 25,502 with this equipment. And the remaining 18% would be given to the latent load, 5,898. And if you look on the top, you'll see our total needs for this home at 25,855 sensible, 4,995 latent. So this piece of equipment is a perfect fit for operation for this home at those temperatures. In a moment I talk about incorrect blower speeds. I want to let you know it's for the Omaha area, the Midwest region where we have certain temperatures and humidities. You might be in an area with incredibly low humidity, like in my Colorado branches where the humidity is low, and my West Nebraska branches where my humidity is incredibly low. They don't worry about the latent load. So their sensible heat ratio, it will be sped up. It may be closer to 0.9 than a 0.8 to get more of the sensible load. They're not concerned with the latent side. Now let's take a look at the incorrect blower speed. This is not necessarily an ESP problem, but can certainly be affected by the ESP. If we're moving 1,350 CFM, our sensible ratio is now 0.86, which means 27,606 BTUs and 4,494 latent. Although we can take care of the sensible load, our humidity draw would be less than the needs of this home. Take a quick look at lower blower speed because of high static. You'll see our sensible heat ratio is a 0.79. Now our total sensible removal is 22,673, and our latent removal is now 6,027. Easily take care of the latent removal, but we no longer have enough to take care of our sensible load. Not only do we need the proper external static pressure on our modulating blowers, we need to know the external static pressure in order to set the proper airflow on most equipment. And you'll see here just that small change of airflow in the total BTUs is 9% difference. Sensible BTUs can be 18% or latent 26% different in our readings. We can look at different items that affect our external static pressure. Here shown as a quick breakdown, we'll see our evaporation coil, our supply diffusers, return grills, filter, balance dampers, and available static pressure is what's left over for our ductwork in this design. And let's look at our components that affect our external static pressure. Here's an example of the same outdoor equipment with ARI numbers using two different evaporation coils. Now, I like to share in class when people come in, when you come to my counter and you ask for an evaporation coil, you tell me a tonnage, a BTU. You might tell me the size. You might tell me it's in a closet. Never do I hear anyone ask me for static pressure. But here's two coils, both the exact same width. One's got a little different height. They're both C-width, 21 inches. And let's look at the static pressure at 1200. CFM, one of them is a 2.43 wet and the other is a 0.143 wet. Drastically different coils. Of course, the cost and the height come into play when people are choosing coils. Likewise with the filter, when people come in, they'll say term high efficiency. They might give me a size. Rarely are doing a static pressure drop. They say I want a 3-ton, a filter big enough for a 3-ton. They don't talk static pressures. But here's a lot of examples. These happen to be Aprilaires, and you see it at 1200. Even in the MERV 13 range, mattering on the quality of the filter, we can go from a fairly low number to a high. And yes, the lower numbers usually are also a little more expensive. And quite often the economics go in the front seat, and we move the proper performance to the back. And here's our two systems. Let's talk about everyone who sits in my chair, or any of you techs out there listening, tech support groups. Get this phone call off, and here's two systems. And look, we chose the more economical but maybe restrictive evaporation coil and filter. And we have a total external static pressure of 0.733. And on our second system, we chose the larger evaporation coil at a 0.143 and a much higher quality filter. And our total external is 0.53. And when we receive this call, it's always the ductwork's fault. And you can see these both have really good ductwork at a 0.1. As a matter of fact, they have identical ductwork between the two of them. Here we are looking at a modulating blower working with a inverter. Yes, the blower is going to set its own speed, but we need to have the proper external static pressure to operate, which most ratings are 0.5. And you'll see the two coils you have, a C width and a B width. And there's nothing wrong with expanding from a B width to a C width. We like the flush fit, but sometimes gaining that little less static pressure helps us choose a better filter. Especially when we take out talking a high efficiency filter and the numbers we have listed aren't loaded. Once we load that up with some dirt, our external static pressure will increase. All right, that small section in the center here with the expanded rating showing you why airflow is so critically important, played a big part in our ESP. The external static pressure must be read, the CFM must be set correctly. Even with modulating equipment, the ESP has to be correct to assure that blower is moving the proper airflow for operation.